For this problem, we're going to first of all prove a statement of the form for all x in x, p of x. And to do that, we're going to let x be an arbitrary element of x, so that's a given. And then we're going to prove that p of x is true for that arbitrary value of x. And then inside of that, we're going to have a goal of the form there exists x in x such that p of x. And we're going to use the first method here to prove that. And the way we do it is we say what we think a good value of x is, represented by a here, but we'll see what it is in our case. And then for that particular value of x, we have to show two things, namely that it is in the set x and that p of x does hold for that value of x. Okay, so let's see how that plays out. We're supposed to prove that for every real number x, if x is greater than 2, then there's a real number y such that y plus 1 over y equals x. Now if you wanted to visualize this, we could draw a graph of this somehow and then look at sort of what happens to the right of the line x equals 2 on that graph. But I'm not going to attempt that by hand. I encourage you to try it out and see what happens. Let's just think through the logic of how to prove this statement. Here's the goal. All right, for every x in the set of real numbers, if x is greater than 2, then there exists a real number y such that y plus 1 over y equals x. Okay, and that goal, it's a universal statement, and so we can take x to be arbitrary, but not completely arbitrary. We can assume that it is a real number, so x in R becomes a given, and then we have this conditional statement as a goal. And to prove that, we can do a direct proof. We can bring our antecedent x greater than 2 over as a given, which leaves us with an existential statement as a goal. And to prove that, well, we have to decide which value of y we think will work. Okay, so we need to find a real number y such that y plus 1 over y equals x. And if I asked you to do that in high school, say, I'm sure you could do it. You just solve this equation for y, right? So when you do that, here's what you get. Y equals square root of x squared over 4 minus 1 plus x over 2. So that's going to be given. We're going to sort of let y equal that. And then we have to prove that that y is a real number, right? And that this equation holds. Okay. So let's try to prove it's a real number first. And this is what we have to work with, right? That x is greater than 2. And so for this to be real, we need to make sure that the thing under the square root is greater than or equal to 0. So we need to kind of build up x squared over 4 minus 1. So first we could square both sides to get x squared greater than 4. And then divide both sides by 4. X squared over 4 greater than 1. And then finally subtract 1 from each side. And we get what we were hoping for, namely that this thing under the square root sign is positive. And so that's a real number, and then x again is a real number from way up here. We can divide real numbers by 2 and add them to other real numbers, and we still get a real number. So putting all of this together, we see that y is in R. Okay. Now we've got to prove that the equation holds. And well, you might already believe it does because we sort of solved that equation to come up with this y, but we need to prove it in a forwards direction. And so all we do is take our value of y and plug it in for y in y over 1 plus y, and we hope that this somehow simplifies to x. Okay. So let's see. To deal with the square root in the denominator here, we want to multiply the top and the bottom of that fraction by the conjugate of the denominator, which is what you see in the numerator here. You just replace that plus sign by a minus sign. And then the denominator becomes a difference of squares pattern. And you see that the x squared over 4's cancel, and you just have a negative 1. So I will take that minus sign and move it right here. And then we're left with just the numerator there. And then you see the square roots go away. And we're just left with x over 2 plus x over 2, which, lo and behold, is x. So we have our goal. All right, let's write this thing up. So first of all, we let x be an arbitrary real number. which left us with this goal. And then I'm actually going to combine two things in the first line. Right? We also assumed that x was greater than 2 to prove this conditional statement, which left us with this as a goal. So here's how we can write those at the same time. We'll say let x be an arbitrary real number, okay, but not any arbitrary real number. Arbitrary real number is such that x is greater than 2. Okay, and then we're going to show that there exists some y in the real numbers such that y plus 1 over y equals x. Great. And now to prove this existential statement, we had to choose a value for y. And here's what we did. And then we needed to prove that y was a real number, and then this equation holds. So we can say let y equal the square root of x squared over 4 minus 1 plus x over 2. And then to prove that it's a real number, we went from x greater than 2 and we did some algebra, right? And eventually concluded that y was real. So I'll just say because x is greater than 2, we have, well, x squared greater than 4. And then it follows from that x squared over 4 minus 1 is greater than 0, putting a couple steps together there. And therefore, combining that with our definition of y up here, we see that y is indeed a real number. Okay. And maybe we should remind our reader what our next goal is. So it remains to check that y plus 1 over y is equal to x. And, well, we got to compute that, right? Y plus 1 over y is this, which is this, which is this, which eventually is that, which was our goal. So I'll just say we compute. I don't want to narrate every little detail there. We'll assume our reader can understand our algebra. And poof, there it is. Okay. So you notice that instead of writing a bunch of equations one after the other, I just made sort of a string of equalities here. Okay, so y plus 1 over y equals this, which equals this, which equals this, which equals x. That's a nice way to write it. And that does it for our proof.